Hey, Wizards. So I wanted to introduce hypothesis testing to you by kind of going back to the beginnings and tracing the development of a sampling distribution and how we modify it and use it for other things, leading up to hypothesis testing. So it all goes back to the sampling distribution of a proportion. So if you recall, let's pretend our population that we have is a all cereal that is berry colossal crunch, and that suppose the population proportion of berries is 0.5, so 50%. 50% of my cereal is berries. Suppose I take a good sample. I take a cupful that has 80 pieces of cereal in it, and in that cup of cereal, 40% of my cup is berries. Now, by a good sample, remember, a good sample means that the pieces of cereal are independent of each other, whether or not they're berries, and that is typically accomplished by taking a random sample. In the cup, to be big enough, I want to make sure there are at least 10 successes and 10 failures. So in this context, my cup has at least 10 berries and at least 10 non-berries. And of course, the sample is not too large. I would imagine a cup full of 80 pieces of cereal is less than 10% of all the cereal in the population. So I take that good sample and I make a dot plot, and I keep repeating this. Sample, dot plot, sample, dot plot, sample, dot plot. I do this over and over and over again, and the central limit theorem tells us is that this dot plot will be somewhat bell-shaped, and that bell shape can be described by this model, where the mean is 0.5, which is what our population is, and the standard deviation is 0.5 times 0.5 over the square root of the sample size, which is 80, or over 80 square root of that. And that turns out to be 0.056. Now we went from a sampling distribution to a confidence interval. So in a confidence interval, all I have is my sample. So I take one good sample, and again, I want it to be randomly selected. I'd like there to be more than 10 berries and 10 non-berries in my cup. And certainly the number of 80 pieces of cereal is less than 10% of all the cereal. So again, in my cup, 40% of the cup was berries. This is all I have. All I have is a cup of cereal, but it's a good sample. I've checked the conditions, so I'm going to use this sample to build my model. So my model now becomes a normal model with a mean of 0.4 and a standard error. This is the standard error of p hat because I'm using my sample to build it. So it is 0.4 times 0.6 over the square root of my over 80, and then I take the square root of that. And so we build our model here. We build our model, and we typically like to grab the middle 95% of that model, and we create an interval for that. And so that interval, I am 95% confident that the true proportion, population proportion of berries is between 29.26% and 50.74%. Now, hypothesis test is kind of the other side of the coin from a confidence interval. In a confidence interval, I stand at my sample and gaze out towards the population, and I don't know if the population is in my interval or not. In a hypothesis test, I stand at my population and I look out at the sample and I wonder, is my sample unusual, odd, or extraordinary? Is my sample way far away from what I think the mean of my population is? So in a hypothesis test, I believe that the cereal is 50% berries. My good sample, though, had 40% berries. So seeing this sample of 40% berries makes me question my belief that the cereal is 50% berries. It makes me a bit skeptical. So I wonder, is the proportion of berries really less than 50%? Or would a sample of 80 pieces of cereal having 40 berries be likely to happen by chance or just by sampling variability? So there are two competing hypotheses here. My first one is the null hypothesis, which says that the population proportion is actually 0.5, just like I believed it to be. My alternate hypothesis, in this case, I will go by with what my sample suggests. Since my sample of 40% berries is less than my population proportion, or what I believe my population proportion to be, since it's less than 0.5, I'm going to suggest that actually the proportion is less than 50%. That's my alternate hypothesis. So in a hypothesis test, I stand at my sample or at my population proportion. So I use what we believe to be true about the population and I build our model. So I believe that the proportion in the population of berries is 0.5, but because I have this sample that has 0.4 in it, I'm a little skeptical. But I still use my population proportion. I use my population proportion to build that normal model. And then in the normal model, I'm interested, how likely is it to see 40% or less berries in a sample of 80 if there really are 50% berries in the population? So I want to find out what that probability is. So in my hypothesis test looks something like this to begin with. My null hypothesis is always a statement about the population. In fact, both of these things are, the null hypothesis and the alternate. But my null always says something is equal to something, so my proportion is equal to 0.5. My alternate says that the proportion is less than 0.5. My sample had a size of 80 and a p-hat of 0.4. So I believe in this model here. That's my model I believe in. It's based on the proportion. And what I'm interested in is that probability, or remember what is called a p-value. So using my normal CDF, I come up with a p-value of 0.037. Looking at this a couple of other ways, I can compute a z-score. The z-score may or may not contradict. That doesn't seem like a very large z-score, but it's closer to -2 than it is to -1. So it does provide us a little bit of evidence that maybe our sample is unusual or out of the ordinary. And if I use my 0.5 to build a confidence interval, my confidence interval goes from 0.39 to 0.61 using my population proportion. That's like the middle 95% of my model. And notice that 0.4 is right at that extreme end of the interval. So this is one of those things that could go either way, but based on our p-value, I would reject my null hypothesis. So kids, that's kind of summarizes what we talked about in class on Monday. And we're going to keep revisiting these ideas throughout the rest of the week, and I will do my best to try to create a short video about everything we do each day during the week, and I hope this video helps.